Well, welcome back, and welcome to our last pre-section video for Calculus 1. We're in the last section. The last section deals with antiderivatives, the idea of going backwards. All semester long, we have been giving you a function asking you what is the derivative of this guy. Granted, we've been doing word problems and stuff in terms of calculate the rate of change of this particular function through word problems and related rates, optimization, take derivative, set equals 0. But it's always the idea that we give you the function and you take the derivative using all the derivative rules you have memorized. But now we're going to be starting to work in reverse. And this is where Calculus 2 really begins at. The idea of the antiderivative. So this time, we're switching up the game. This time, we are going to be giving you the derivative and asking you what the original function is. It's called the antiderivative, or pretty much going in reverse. So, for example, the derivative of x squared is 2x. Therefore, the antiderivative of 2x is x squared plus c. Why plus c? Because the derivative of a constant is 0. So the antiderivative of 0 would be just a constant, but I'm not sure what that constant is going to be. So anytime you're doing antiderivatives, you always have this plus c aspect for the ability to take the antiderivative of a constant, antiderivative of 0, which gives you the constant. So it is, again, the whole idea in general, reverse of the basic rules of differentiation. So as there were rules for all the derivatives you have memorized, there are rules for all the antiderivative, and another word for antiderivative is the word integral. The integrals of this thing. So when you hear the word integral or antiderivative, it means the same thing. So the integral or antiderivative of x to the n dx is, well, let's think about this. The derivative of x to the n was n out front, x, and then you subtract 1, n minus 1. But now that I want to go in reverse, I want to do the exact opposite. The exact opposite of subtracting 1 from the exponent would be adding 1 to the exponent. And the opposite of putting it out front as a coefficient would be putting it to the denominator as a coefficient. So the antiderivative or integral of x to the n dx would be equal to x to the n plus 1 over n plus 1, add 1 to the exponent over add 1, plus c, because every function has a plus 0, so the antiderivative of 0 is where this plus c thing comes from. And this formula works for any, it's called the power rule, for any x raised to any power except negative 1. We'll talk about him in just a second. So let's look at some of your other basic rules here. Well, since the derivative of e to the x is e to the x, the antiderivative of e to the x is also e to the x. This would be the integral or antiderivative of e to the x with respect to x. This is what that dx stands for. With respect to x. That tells you what the variable is in your particular problem. So if I integrate integral of 5 dx, that's going to be 5x. So I can write down another rule here. The integral of a constant dx is equal to a constant times x plus c. But that at least told me what the variable had to be. I can also have dt's on a problem, so the t is going to be a variable. Or later on, we get you into Calculus 3, we'll have multivariable calculus, and this will tell me what the variable that I'm interested in. So whether it's x, y, z, t, w, whatever. So the integral of e to the x dx is e to the x plus c. The integral of a to the x dx, a to the x with respect to x, so x is my variable, would be a to the x divided by the natural log of a plus c. Well, since the derivative of the natural log of x is 1 over x, therefore the antiderivative or integral of 1 over x dx is going to be the natural log, and officially we write absolute value to remind us we can only take the natural logs of positive numbers, plus c. And if you'll notice, this is when x is equal to negative 1. If you clean this up, 1 over x, same thing as x to negative 1, so that's a special rule. That's one we put up here, as long as x was not, as long as n was not equal to negative 1. Also, don't forget those little arctangent formulas. So the derivative of arctangent of x is 1 over 1 plus x squared. Therefore, the antiderivative of 1 over 1 plus x squared dx is the arctangent of x plus c. The derivative of the arcsine of x was 1 over the square root of 1 minus x squared. Therefore, the integral, antiderivative, integral of 1 over the square root of 1 minus x squared dx is the arctangent of x plus c. So really, I have all these rules memorized from the derivative. I'm just rewriting them in an antiderivative fashion, and that's what this section is all about. Also, you got your 6 trig functions here. The derivative of sine of x was cosine of x. Therefore, the antiderivative of, or integral of the cosine of x dx is the sine of x plus c, rewriting the form in reverse. Therefore, the integral of sine of x dx is equal to negative cosine of x dx. The integral, or antiderivative of secant squared of x dx is equal to the tangent of x plus c. And let's just remind ourselves, the derivative tangent of x is secant squared of x. Therefore, the antiderivative, or integral of secant squared of x dx is back to tangent of x plus c. The antiderivative, or integral of secant squared of x dx is equal to negative cotangent of x plus c. Since the derivative of secant of x is secant of x tangent of x, therefore the integral of secant of x tangent of x dx is equal to the secant of x plus c. It's all my derivative rules just written in the antiderivative format. And last one, the integral of secant of x, integral of cosecant of x cotangent of x dx is equal to negative cosecant of x plus c. This is classic proper notation, and when you're doing antiderivatives, don't forget to put that old plus c on there. So, let's see if we can take these rules and apply them. Now, first one, try to make it pretty simple for you. So, here we go. Examples of the, find the antiderivative for the following function. So the antiderivative would be antiderivative or integral of 5x cubed minus 15x squared plus 14x minus 7 dx, because x is my variable of my function here. So this is what the dx tells me back here. Now, just like with derivatives, when I took a derivative of a bunch of things being added or subtracted, I took derivative of each one. When I take the antiderivative of a bunch of functions that are the terms that are being added or subtracted, I take the antiderivative of each one. That'll be the integral of 5x cubed dx minus the integral of 15x squared dx plus the integral of 14x dx minus the integral of 7 dx. Now let's integrate. Integrating this thing, constants hold over, just like with derivatives. Leave the constant. You're integrating x to a power. Remember, the rule for x to a power is you add 1 over add 1. So this will be x to the 4th over 4. Again, there'll be a plus c, but there'll be a plus c for each term. So a constant plus a constant plus a constant plus a constant. At the end of the day, will be just one big constant. We'll put one big plus c on this thing. Minus 15 is a constant. Hold over. What's the integral of x squared? Add 1 over add 1 is x cubed over 3. Plus 14 is a constant. Hold over. This is x to the first power. Integral x to the first power. Add 1 over add 1. X squared over 2 minus, and the integral of 7 dx, and I wrote that special rule up here, integral of a constant dx is just a constant times x. So the integral of 7 dx is 7x, and plus c plus c plus c plus c is one big plus c. So this is equal to 5/4 x to the 4th minus 15 divided by 3 is 5, x cubed plus 7x squared minus 7x plus c. And you're taking your first antiderivative. Now, if you really wanted to double check yourself, because new rules and the like, you can take the derivative of this term, of this function, and you should get this answer back again. Well, let's see. 5/4 x to the 4th. Derivative of that, bring down the 4. The 4's cancel. And x to the subtract 1, 3. That'll be 5x cubed. Minus the derivative of 5x cubed is going to be 15x squared. That matches up. The plus the derivative of 7x squared is going to be 14x. That matches up. The derivative of minus 7x is minus 7. That adds up. And derivative of constant is 0, so that went away. So when I took the derivative of this guy, I got my original answer back. It's a great way of checking. But just like with derivatives, antiderivatives have the same rule. So let's apply this. We're supposed to find the antiderivative of this guy, so we're going to integrate 20x to the 1/2 minus 16x to the 3/4 with respect to x to find the antiderivative. Now, you can write this integral each term, but basically we just do this in our head. Integrate each term. And terms are separated by addition and subtraction. So when you've got a bunch of adding and subtraction, just integrate each one. 20 is a constant. Constants hold over. What's the antiderivative or integral of x to the half? The rule of x to a power is add 1 over add 1. That'll be x to the adding 1 to a half is 3 halves over 3 halves. We'll clean them up in a minute. Minus 16. This is x to the 3/4. So we add 1 plus 3/4 is 7/4 over 7/4. And you always have, every time you integrate a plus c and got multiple terms being integrated, one big plus c at the end. Okay, so, and you can clean this guy up by inverting and multiplying. So when you divide by a fraction, invert, multiply, that'll be 40/3 x to the 3 halves. Minus, when I invert and multiply this guy, I'm going to get 4 times 16, which is 64. So this would be minus 64 over 7, x to the 7/4 plus c. And there's my solution. And again, as you start out, the more problems you do, the better, more comfortable you get with this stuff. But if I take the derivative of this guy, I'll get that answer back again. Look at the next guy. Again, same directions here. You want to find the antiderivative of this guy. So here we go. We're going to integrate the 5th root of x squared plus 12 over x to the 5th plus 1 over x dx. Well, here's the big rule about this stuff. Clean it up first. Just like with derivatives you had to clean it up, with antiderivatives you also have to clean it up. So I don't do 5th roots. So this would be the integral. 5th root is a 1/5 power of x squared. When you clean it up using your exponential properties, that's x to the 2/5. Plus, I don't like stuff on the bottom. I bring it to the top and make it negative. That'll be 12x to the -5. Plus, now 1 over x is a special function that I have memorized. The integral or antiderivative of 1 over x is natural log of the absolute value of x. So I'm going to leave that guy alone because I know that's a special rule. Now we apply our rules. X to a power, you integrate, you add 1. Adding 1 to 2/5 is 7/5 over 7/5. Add 1 over add 1. X to a power, add 1 to the power over that power. Plus 12 is a constant, leave it alone. X to the add 1. What is plus the -5 plus 1? It's actually -4 over that power, -4. Plus, what's the integral or antiderivative of 1 over x? That's a special rule. That was the natural log of the absolute value of x. And then one big plus c for integrating. Everything has plus 0 times. You always have a plus c. Now let's clean this guy up. When I divide by a fraction, invert, multiply, that'll be 5/7 x to the 7/5. 12 divided by -4 is -3. If I wanted to clean them up, I can just leave them x to -4, or I could put it over x to the +4 if I clean them up. Plus the natural log absolute value of x plus c, and there is my antiderivative. Again, what I'm literally doing here is applying these rules. So just like you had all those derivative rules memorized, you're going to have these antiderivative rules memorized. Well, these are just working these first basic ones. Let's see if we can get some more advanced problems. Okay, take a look at number 4 here. You're supposed to, again, same directions. Find the antiderivative of this particular function. So we want to do the integral of 2x to the 4th plus 6x, I don't do square roots, that's a half a power, over x squared dx. But my problem with this guy is we don't have a quotient rule that we have memorized in terms of all the rules we have right here. These are all the basic rules. These are the ones we want to have you guys memorize. And there is no integrating of fractions here except for these special arctangent and arcsecant guys. So you got to go back to your basic algebra. Clean it up first. Since we're dividing by a single denominator, same thing as what we did with derivatives. Clean up the algebra first. When you divide by a single term, you can take everybody in the numerator. In this case, it'll be 2x to the 4th divided by x squared plus 6x to the half divided by x squared, and divide each term by that. Cleans it up, but just like with Calculus 1, this beginning of Calculus 2 stuff here, a lot of algebra. Got to clean it up first. X to the fourth divided by x squared is x squared, so that'll be the integral of 2x squared plus 6. X to the half divided by x squared. When you divide fractions, when you divide terms, you subtract their exponent. A half minus 2 is x to the negative 3 halves dx. All that, you actually didn't do any calculus at all. What you've actually have done here is cleaned it up to a point where I can apply one of my rules. 2 is a constant, leave it alone. The integral x squared, integral x to a power, x to the n, you add 1 over add 1, x to n plus 1 over n plus 1. That makes it x cubed over 3. Plus 6 is a constant, leave it alone. Well, x to the negative 2/3 power, x to a power, you add 1. Adding 1 to negative 3 halves is going to be x to the negative 3 halves. Add 1 to that would be x to the negative 1 half over negative 1 half. And of course, that's 2 terms there, so plus c, plus a constant here, plus a constant here, one big constant. Of course, you want to clean this guy up, so your final solution is going to be 2/3 x cubed. 6 divided by negative a half, you invert and multiply, that'll be minus 12x to the negative 1 half plus c. Or for you guys that are big fans of the back of the book, you'll probably see this. 2/3 x cubed minus 12 over the square root of x plus c. Now where did I get that 12 over the square root of x? Negative exponent goes on the bottom, and a half a power is a square root. Of course, you've got to memorize your trig forms. Same directions, find the antiderivative or find the integral. The integral of 10 tangent of x plus 6 cosine of x dx. This is equal to, just to let you know, same idea. If terms are being added or subtracted, I integrate each one, and constants get to go out front. So another way I could have written this would be 10 times the integral of the tangent of x. Nope, let me do that. I made a typo on this one. Let me make it one of the forms we have memorized. This was supposed to be a secant there. That was my typo when I type out my notes. This will be a secant. Squared. That's what I was after. Of x plus dx plus 6 integral of the cosine of x dx. This was a typo before I started this problem because the integral of tangent isn't one we have memorized. The derivative of tangent we have, but it's the integral of secant squared is the tangent. That's actually what I meant to type up there. So here we go, as we analyze this stuff. So again, it will be a rule that we have memorized. We're just going to go for the basic rules. Calculus 2, the whole goal of Calculus 2 is to get you guys into more and more advanced antiderivative forms as you go through the class. So this is the function was m of x was equal to 10 times the secant squared of x plus 6 cosine of x. Well, and again, just like with any antiderivative, you're going to integrate this guy, and constants go out front, and I can distribute these integrals in the dx's because we're integrating with respect to x here. 10 is a constant. What was the integral of secant squared of x? Well, that was the rule that I wanted you guys to have memorized here. The integral of secant squared of x dx is tangent of x, so that would be equal to 10 tangent of x plus 6. Now what is the integral of cosine of x? So I'll go back to my rules over here. The integral of cosine of x is sine of x. And then one big old plus c. So your final answer is 10 tangent of x plus 6 sine of x plus c. Okay? Again, other different ways we could word this. Same directions though. Find the general antiderivative of big F of x. Antiderivative f of x if little f of x is equal to 7 over 1 plus x squared. A little rule about this stuff is this. When I integrate little f of x dx, when you integrate, or take the antiderivative of it, you add 1 over add 1. So when you're integrating, you're actually making bigger functions. And we're math people, so don't think too deep in our notation here. So we integrate a little f of x, since you make the function bigger by adding 1 over adding 1 on your general power rule there. That's when we call it big f of x plus c. So here's a general rule that we write with antiderivatives. When you integrate little functions, you get big functions back again, because when you integrate something, you make the function bigger. So all you're really supposed to do with this problem is integrate 7 over 1 plus x squared dx. 7 is a constant. It's on top, but you can pull it out. That'll be 7 times integral of 1 over 1 plus x squared dx. And that's equal to 7 times, 1 over 1 plus x squared. When you integrate that, that's one of those special rules. It was the derivative of the arctangent. So the integral of 1 over 1 plus x squared dx is the arctangent of x plus c. And this is what they're looking for, and they would call this big f of x equals. Okay? And again, where that rule is coming from is right here. The integral of 1 over 1 plus x squared dx is equal to the arctangent of x plus c. Okay? And let's do one more, and just a little bit more elaborate type of problem that you guys can do, and that is this one here. Find the antiderivative of f of x equals 2x to the 7th minus 4x cubed, and f of 0 equals 9. Something new has been added, and I'll talk about that in a second. But let's do the first thing. Find the antiderivative of this guy. Well, remember, the antiderivative of little f of x dx is equal to big f of x plus c. So, I'm supposed to take the antiderivative of 2x to the 7th minus 4x cubed dx. And what that's going to do, when you integrate a little function, you get the big function back again. So this is what they're talking about. Big f of x, since this was called little f of x, big f of x would be the antiderivative of this function. Well, 2 is a constant, hold over. What's the integral of x to the 7th? Add 1 over add 1 gives you x to the 8th over 8. Minus 4 is a constant, leave it alone. Integral of x cubed, add 1 over add 1 is x to the 4th over 4. And of course, every time you integrate, you get a plus c plus another constant, one big plus c at the end of the problem. You clean it up so you get this. F of x is equal to, well, 2 goes to 8 4 times. That'll be x to the 8th over 4. Minus here, the 4 is canceled. That's just x to the 4th plus c. And there's your answer. But there's this extra little part here, and that's something worth noting here. So every time I take an antiderivative, I get this plus c. But if I want a particular solution, they got to tell me at least one little piece of the puzzle about the original function. Here they're telling me f of 0 equals 9. This information here is to help solve for that plus c constant. What exactly is that constant that you are trying to, every time you integrate, you put a plus c on? We'll plug it in. F of 0 would be equal to 0 to the 8th over 4 minus 0 to the 4th plus c. All I'm doing is replacing x with 0, but that's supposed to be equal to 9. Well, 0 to the 8th is 0 divided by 4 is 0. 0 to the 4th is 0 plus c is c, must be equal to 9. Therefore, your final solution is f of x equals, what was my function? It was x to the 8th over 4 minus x to the 4th plus c, but c is 9. This is the particular antiderivative of this particular function that actually goes through, this is the antiderivative of this particular function that goes to the point f of 0 equals 9. This function here. When I plug in 0, I get 9, and when I take the derivative of this guy, I'm going to get 2x to the 7th minus 4x cubed. We're doing antiderivatives. That's what chapter 4.7, the last section of your Calculus 1, is all about. But it's very important in the sense that this is where Calculus 2 begins. The concept of the antiderivative. And all semester long we work on antiderivative or integrals. get used to being called integrals, and that's what that big elongated S guy is called, the integral of these functions, or the antiderivative of these functions. Because, and like I said before, in Calculus 1, we gave you, here's a function, we asked what the derivative is, and made you do all the applications of that stuff. In Calculus 2, which is what this is at the beginning of, we're going to give you the derivative. They give you the derivative and ask you what the antiderivative of. What was the function originally that when I took its derivative, I got my answer. So we're working backwards now. So I hope you enjoyed Calculus 1. Like I said, this is the last section, so study hard, and we'll see you in Calculus 2.